So, welcome back to this class on hardware security. So, we shall be continuing our discussion on branch prediction attacks. In particular, we shall be trying to see how the branch predictions or discussions on branch predictions can be used or leveraged to actually perform an attack on public key crypto systems. In particular, in the last class, we saw that there was a nice correlation that we observed between the system branch prediction and our simple approximate model, which is the 2-bit counter model. So, the question is whether we can utilize it to attack an actual implementation of a cryptographic algorithm. So, we shall be considering an RSA implementation and an elliptic curve cryptographic implementation, and we shall be trying to illustrate how an attack works. So, let us consider the classic algorithm for modular exponentiation as our target. So, in this particular algorithm, right, we are the input m is encrypted or decrypted by performing modular exponentiation with the modulus n on public or private keys represented as an n-bit string. And this algorithm is essentially nothing but an implementation based on the simple square and multiply exponentiation algorithm. The idea is that here we basically perform a so the idea is that we basically perform a squaring, and the squaring is essentially kind of observed as s into s modulo n. So, this is something that we always do, whereas if the secret bit is 1, that means if your secret bit di is 1, so this is your ith secret bit, then we actually do a additional multiplication. That means we basically take s and we multiply s with m. So, that is your s into m modulo n operation. So, the final objective is to calculate say m power of d, where d has been elaborated in the form of a binary exponent. So, conditional execution of instructions and their dependence on secret exponent is exploited, as we have already seen, by simple power and timing side channels. So, here we will see that how we can perform a branch misprediction attack on these kind of implementations. So, we will start with this and we will gradually go into slightly more improvements. So, the improvement that we will be considering is essentially a very popular exponentiation primitive for asymmetric key cryptographic algorithms, which is essentially called as the Montgomery ladder algorithm. So, the Montgomery ladder algorithm is essentially, as you can observe, that as opposed to the previous implementation where there was only one register, that is the register S. So, now there are two registers. So, we have got the register R0 and R1. We initialize R0 to 1 and R1 to M. So, the idea here is that we basically make R0 as 1 and R1 as M, and the ratio, that is of R1 and R0, which is here M, essentially remains an invariant through this entire loop. So, this basically does not change. So, this invariance can be observed here. For example, if the di is 0, like if the secret ith bit is 0, then you basically multiply R1 in R1, that means you basically perform. So, the idea is that if di is 0, you basically calculate R1 as R1 multiplied by R0. Of course, like everything is modulo n, so I am not writing the modulo n part. And if and also right, what you do is you basically do a squaring in R0. So, R0 becomes R0 squared. So, here you can observe that if you calculate R1 by R0, so that remains as R1 into R0 divided by R0 squared. So, that remains as R1 by R0, but in the previous iteration. So, let me write this as I minus 1, and this is your ith iteration output. Likewise, right, if your secret bit is 1, that is di is 1, then you perform multiplication in R0. So, therefore, R0 becomes R0 into R1, and you perform squaring in R1. So, R1 becomes R1 squared. Again, you observe that R1 by R0 in the ith iteration is same as that of R1 by R0 in the previous iteration. Okay. So, therefore, right, at the end of the day, we basically ensured that through this computation you return the value of R0, and the value of R0 is indeed equal to like m to the power of d modulo n, which is essentially what we want. But at every iteration you are performing both squaring and multiplication. So, therefore, this is a more secured algorithm, or at least it is more secured against simple power attacks or simple side channels. And it is also timing attack resistance, in the sense like it is it does not have a time variance as we have seen in the previous case, because you are performing a multiplication and squaring in both the cases. Okay. So, it is essentially having a balanced, it's a more balanced exponential technique compared to the naive square and multiply algorithm. So, now we shall be seeing, right, essentially a very popular way of calculating these multiplications, and as you can see that multiplications are inherent to performing the public key algorithms. So, people have developed several architectures for multiplication. One of the very popular multiplication routines is essentially due to what is called as the Montgomery multiplication. So, here we illustrate it is an efficient way of performing multiplication modulo n. So, therefore, there are two arguments a and b, and I want to calculate a into b mod n, where n is essentially a k bit number. So, the idea is that n is essentially a k bit number, and k, as we know, is typically large. So, it could be, for example, 1024 bit or 2048 bit or even larger. So, it is based on, so now this multiplication is based on what is called as Montgomery reduction. So, Montgomery reduction basically chooses a large value of r, but then r essentially is something like 2 power of k, and as you can see that n is a k bit number. So, you can expect that r is larger than n. Okay. So, r is kind of larger than n. Okay. So, r is essentially also observe the form of r, which is essentially 2 power of k, and that makes computation using r quite easy because it is a power of 2. So, in Montgomery reduction, we basically calculate or return the value of T r inverse. Okay. So, T is my input, and I would like to calculate T r inverse when T is restricted between say n r, between 0 to n r. How do we do that is shown here by this algorithm. So, we basically calculate m, which is equal to T into minus n to the power of minus 1 modulo r. So, therefore, we basically calculate n to the power of minus 1. Okay. And then we perform this computation, and then we basically subtract, if this value is greater than equal to n, then we subtract n, and this is my result, and this result is indeed equal to, or the claim is that the result which is returned here is equal to T r to the power of minus 1 modulo n. So, let us try to understand why it works, and the logic is quite simple. So, if you basically cross multiply, so you multiply T and r, then you should get the result, right, is essentially T into r, which is equal to, so you can observe here that T is nothing but T plus mn by r. So, if I multiply small t into r, then that is equal to T plus mn. So, if I now take modulo n, then this basically goes to 0, therefore, I have only T, okay, and that basically establishes this fact. Also note, because it is important to observe, note that why is this an integer, because as I said that I have done just this division, right, n T plus mn divided by r. So, you observe that T plus mn is equal to T plus T into minus n to the power of minus 1 n, because m is essentially equal to T into minus n to the power of minus 1 modulo r. Okay. So, therefore, right, if I do a modulo r operation, then this part essentially is 1, and therefore, or minus 1, and therefore, I get T minus T, which is equal to 0, which means that r divides T plus mn. Okay. And therefore, right, T plus mn divided by r is an integer. Okay. And also observe that I have done here one subtraction with n. Why one subtraction with n suffices? So, the idea is that you observe that m is essentially between 0 to r. This you can easily observe because you are doing a modulo r operation. So, m is between 0 to r, and therefore, if I multiply with n, then I get 0 is less than equal to mn is less than rn. So, this number is less than rn, and also observe t is less than rn, and therefore, right, when I add t plus mn, then this value is less than 2 rn. That means, right, T plus mn divided by r is less than 2n. So, therefore, this number does not exceed n, and therefore, right, it does not exceed 2n. So, therefore, in order to do or bring the result modulo n, because finally we have to bring the result modulo n, we have to do at most one subtraction with n. And therefore, right, this is a very common way of doing the Montgomery reduction, and many libraries actually does this extra reduction operation, and this is exactly what we will be targeting in our attack. So, this if statement is what we will be targeting in our attack description. So, just to complete this part, how we can use this to perform multiplication can be just observed by in this slide. So, the idea is that what we do is shown here, that suppose I want to multiply a and b by using the Montgomery algorithm. So, what we do here is shown over here. So, the idea is that I have got a simple description here. So, what we do is we pick an r, which is say equal to 2 to the power of k, okay, and the idea is that 2 to the power of k and which is r and n, the GCD is 1. So, that means, like as we have already seen, n to the power of minus 1 modulo r exists, and we have computed that. So, what we do is we compute a dash, which is equal to a into r, and we compute b dash, which is equal to b into r, and this is called as Montgomery reduction. That means or Montgomery transformation. That means we transform a to the Montgomery domain and call it say a dash or maybe a, okay, and we transform B into the Montgomery domain, and that is called as B. So, idea is A is nothing but A into R modulo n, and B is again B into R modulo n. Okay. So, you can observe that as we have in the previous case, we have seen that suppose I like I have got a simple routine of calculating. So, if I give you an input, for example, as we have seen in the previous case, where the input is for example, what we get is t into r to the power of minus 1. So, therefore, what I can do over here is, if I call that routine and I pass a and r square. So, if I pass like a and r square as an input, then I would get the result as a into r square. So, basically like this is my result. So, basically I would get a into r square to the power of r to the power of minus 1, okay, and that is equal to a into r. Okay. So, then we basically also we perform the Montgomery multiplication with b and r square, and I get the result which is b into r square with r to the power of minus 1, and that is b into r. Okay. So, then we perform a Montgomery multiplication, and the Montgomery multiplication is essentially shown over here as like perform with a and b. So, the idea is that a is your a into r. So, we basically perform or multiply a into r with b into r, and with r to the power of minus 1. So, that becomes your abr, okay, and then we basically again call this routine abr with 1. So, you can see that this is Montgomery multiplication is with 1. So, we basically multiply abr with 1 and with r inverse, and that is equal to a into b. Okay. So, we basically need a way of calculating essentially a into b into r to the power of minus 1, and with that routine we essentially can calculate a into b, okay, as shown over in this part. You also observe that like once we have the inputs in the Montgomery domain. So, if you perform the Montgomery reduction, so and if you just take this a dash and if you take this b dash, then if you are given this a dash into b dash, okay, then the Montgomery reduction gives you the value of a dash into b dash r to the power of minus 1, okay, because the moment you are, as we have seen in the previous case, that if you are given t, right, you basically get t into r to the power of minus 1 modulo n. Okay. So, likewise, right, you can perform a sequence of Montgomery reductions and you can obtain the corresponding results here, and that pretty much gives you the corresponding Montgomery multiplication just by doing Montgomery reductions. Okay. And therefore, right, why it is very efficient, because the moment you have got r as in the form of 2 to the power of k, the assumption is that multiplication with r, division with r, and modulo with r are trivial operations. They are much more easier than doing modulo n operations. Okay. So, therefore, right, I mean this is essentially the working of the Montgomery operation. So, now the question is, right, if you have got a kind of library where essentially which essentially uses Montgomery multiplication, there is a high probability, or at least you should be careful if there is a routine as shown here, where the Montgomery multiplication is using a Montgomery reduction where there is this kind of conditional statement. Okay. And that is exactly what we will be targeting in our attack description. So, the overview of the attack is as follows. The work shows that the HPCs which are used as performance monitors or watchmen in modern computer systems can be utilized to retrieve the secret keys by reasonably modeled adversaries. The attack exploits the characteristics of branch predictor and shows that the leakage of the key increases with the ability of the attacker to model the predictor more accurately. For example, we have made an approximation that there is a nice correlation with a 2-bit predictor. If I have a better model, then I can use that better model, but we will show in most cases, right, the simple model as a 2-bit predictor should be sufficient. We claim that the branch bits from the HPCs are indeed more significant, and they are more significant side channels compared to timing. More details of this work can be observed in this work that is shown here in this paper. So how we should, or rather why should we consider HPCs for security analysis? So, the results from HPCs are treated as an accurate representation of events occurring in hardware. Performance of PUF subsystem has already been allowed in the Linux kernel 2.631 onwards as performance counters for Linux. So, we at this point assume that the adversary can observe the total number of branch misses in an entire decryption operation by using a command like perf_stat -z branch misses. Now, observe that this is the event that you would like to observe, and you basically give any executable at this point. Okay. So now there is system. In the system we are considering that both the user, who is my target, so this is my victim, who is essentially running a decryption code with heavy branches, and also write not only heavy branches, but branches as we have seen in, which depends on the secret. And there is a spy or an attacker which basically runs, say, a multiplication code and observes the parse stat concurrently. So therefore this executable could be the executable of the multiplication code, for example. So then the idea is that if this person, right, is executing a decryption code and there are branch misses, as you can observe in this statistic in this graph, then this essentially is also observable to the attacker or to the spy. So therefore, right, I mean the idea here is that an unprivileged user residing on the same system, who has basically the capability of monitoring these events, can gain access to sensitive information of the privileged. That is what we will illustrate here and show that how we can get the key which essentially the processor or the user is, or the victim is utilizing. So the main point is that the increase or decrease of branch misses of the privileged process can be monitored by the spy, and the present attack exploits the ability to measure the increase or decrease of branch misses rather than actual values. So note that if you observe the plot that we showed in context to correlation, we could not, we are not claiming, or it is not that one thing which should be kept in mind is that we are not predicting, like the actual branch misses, but what we are predicting is the relative branch misses, like whether the branch misses are increasing, decreasing, or whether they are remaining constant. So what is more important is the monotonicity of the graph, rather than like whether the actual value of the branch misses. So what we do over here is that in order to explain the attack, we basically monitor the branch misses on the square and multiply and the Montgomery ladder algorithm, using Montgomery multiplication as a subroutine for operations like squaring and multiplication. And the branch miss relies on the ability of the branch predictor to correctly predict the future branch misses which would be taken. And the profiling of the HPCs using performance monitoring tools provides a very simple user interface to different hardware events, and what we are observing here is the branch misses. So in the attack, we will basically considering, say, an n-bit secret scalar. So it could be in either in elliptic curve crypto or in even the RSA exponential as we have seen. Suppose the secret is shown here as k0, k1 and so on till kn minus 1. So it is an n-bit secret that we target. So the trace of the taken or the not taken branches as condition on the scalar bits are expressed as, say, b0, b1 so on till bn minus 1. So these are basically nothing but sequence of taken, not taken, taken and so on. So the idea is that if the key bit is 1, that means if say the kj is 1, then the conditional additional statement in the double and add algorithm gets executed. Okay, so therefore if I get a 1, then I basically execute it, and therefore, right, it implies that when kj is 1, the branch is 0, because I mean the branch outcome is 0, because you are it is essentially resulting in the not taken branch, because you are not taking that branch. Okay. So what I am trying to say is that if you, for example, write like if, say, the ki is or kj is 1, okay, then you are saying, suppose that you essentially execute, okay, for example, a square and say you execute a multiplication step, or what you execute in elliptic curve cryptographic, right, you basically execute, so this is an OR, you execute, say, a double or I mean an addition operation. Okay, so you perform an addition, so execute multiplication or you execute an addition. So the idea is that if the kj is 1, since you are going to the next instruction, that implies that the branch is not taken, and therefore, right, we would say that the bj is equal to 0. On the other hand, if kj is equal to 0, then you basically jump to the next location, and therefore actually the branch takes place, and so you write bj is equal to 1. Okay. So now with this background, you can observe, right, I mean, and it's also important to observe that if you take this kind of codes and run it through several compiler optimizations like O1, O2 and O3, then you will still find that these kind of instructions will remain in your final target code, and therefore, right, the idea is that the assembly generated even using various optimization levels would probably retain these conditional statements that you are writing in your high level program. And that means, right, that understanding and evaluating them with respect to security is of paramount importance. So what we try to do in the attack can be shown here as in the threat model. So again, this is an iterative attack algorithm. So we assume that we know, say, like d0 to di, and what we would like to know is, or we know the first I bits of the private key, and we want to determine the next unknown bit, which is di of the key. So, we generate a trace of branches. So, what we do is that we basically target the underlying Montgomery multiplication of maybe the of maybe the squaring step, because remember that the squaring takes place always. So, therefore, right, we basically target the Montgomery reduction if statement, as I said, which was the target, and we basically kind of target it and basically simulate the trace. That means, like in several whenever like the D0 is if D0 means the first key bit is coming into play, then the next key bit which is D1 which is coming into play, and so on. At every step like D0, D1, D2, D3 and so on, the corresponding if statement in the Montgomery multiplication or the Montgomery reduction is essentially generating a sequence of branches like taken, not taken and so on. Okay. So, this essentially or this history is essentially denoted as the trace of branches, and is essentially is what we basically denote by this tuple Tm1, Tm2 and so on till Tmi. Okay. So, therefore, right, for if so this is for the conditional reduction of the Montgomery multiplication at every squaring operation. So, then we basically make a guess of the ith bit. So, remember that the ith bit can have the value either 0 or 1, and based upon that we basically make a prediction. We basically kind of simulate an appropriate value of Tmi plus 1j, that means the next corresponding branch taken or branch not taken for the conditional reduction of the Montgomery multiplication of again of the squaring step. So, the adversary, remember, can only simulate the branches using its model for any partially known bit. So, this partial simulation can only be performed by using the simple model essentially, which is the 2-bit predictor model that I described, and the adversary does not have any granular control on the HPC values of any sub simulation. So, we basically for the actual system, like for the actual target, we basically can get like a hard count for the branch misses. That means when the entire decryption happened, I get a total count of the decryption. Okay, I get a total count of the number of branch misses, but I do not have a very fine grained control. That means I do not have a control like what happens in every bit of the input, for example. So, therefore, right, but we can use our model to do that partial simulation. Okay. So, now the question is, right, how can we employ this to perform and complete an end-to-end attack. So, therefore, right, what we do can be illustrated here in this diagram. So, this is the offline phase. So, we take or we collect several inputs. So, these are my plain text, and we basically divide my plain text by using an offline phase or in the offline phase. So, what I do is here shown here is that I basically guess this ith bit. So, this ith bit can be either 0 or can be either 1, and I know. So, this is already known. So, this is my prior knowledge. So, I already know say the previous key bits. I make a guess here. So, this guess can be 0 or this guess can be 1. Okay. And note that I also know the trace of this taken not taken, because since I know this d0 d1 till di minus 1, I can calculate, right, this m to the power of d0 till say di minus 1, and I observe the corresponding squaring operation, okay, of the Montgomery reduction. Okay, I mean I observe the corresponding I observe the squaring of the I basically observe the squaring of the the square and multiply algorithm, for example. And in particular, what we observe is the Montgomery reduction. Okay. So, because the squaring, right, will also use or call the Montgomery reduction underneath, and we basically observe the Montgomery reduction, and note that in the Montgomery reduction we had this line, right, which is something like Ti greater than n or Ti greater than equal to n. I basically do a T equal to T minus n operation. So, this is the one, this is the operation which I target, and in particular I target the outcome of this branch, whether the branch is taken or whether the branch is not taken. But in order to understand that, I need to simulate this value of t, and this essentially I can get, or is a function of my previous I minus 1 bits and also on the value of the message. Based upon that, I can simulate these possible sequences. So, now, right, I mean what I do is I basically take my simple 2-bit predictor and I feed my inputs T1 to Ti, for example, and that gives me like a guess of the next outcome. So, if the next outcome and also, right, based upon the value of di equal to 0 or di equal to 1, I can extend this simulation to know what is the actual value of the next outcome of this branch. If the idea is that if my 2-bit predictor correctly gives me the next sequence, that means if there is a match when I am giving T1 to Ti, and if it indeed matches with your Ti plus 1 1. So, Ti plus 1 1 means like essentially is this outcome, for example. Then I put M to the basket M1. So, again I maintain 2 baskets here, call it as M1 and call it as M2. The idea is that if I get that these two are indeed equal, then I put this message M into the bucket M1, or I put M into the bucket M2. Okay. On the other hand, if this is equal to Ti plus 1 0, so that is essentially the other possibility. That means if Di equal to 0, then the outcome here, that means whether this outcome was 0, I mean whether this branch was taken or not taken, is captured by say Ti plus 1 0. Okay. So, if my model, that means if the model T essentially correctly essentially matches with Ti plus 1 0, okay, then I basically take again or define 2 more brackets, call it as M3 and call it as M4, and I put the message. So, if it matches, then I put it into M, or if it does not match, then I put this M into the bucket M4. Okay. So, therefore, I basically kind of partition my input M into these buckets M1, M2, M3 and M4, and I basically, so you see that there are 2 alternatives. This M can go into either M1 or it can go into M2, or this message M can also go into M3 and M4. So, there can be potentially a message M which goes into say M1, okay, or it also goes to say maybe M3, okay, that is also possible. So, we basically kind of in order to kind of improve the accuracy of the attack, what we do is basically we basically do a further step, and we basically ensure that there is no common ciphertext in the sets M1, M3 and M2, M4. Okay. So, note that it may happen that a sequence matches here, okay, and therefore, it goes into M1. Okay. So, now it may also happen that the sequence, so the idea is that if it goes to M3, okay, then it is kind of contradiction, right, because essentially in one case, right, I am predicting that it matches with Ti plus 1 1, and the other case, right, I am saying that it matches with Ti plus 1 0. So, in order to remove that contradiction, I ensure that there is no common ciphertext which goes into M1, M3 and M2, M4, okay, and the sets are ideally disjoint. Okay. And note that what I do is, so therefore, right, I have got now 4 buckets like M1, M2, M3 and M4. The idea is that M1 carries those messages which does not cause a misprediction during the Montgomery multiplication of the I plus 1th squaring if Di is equal to 1, and M2 are those messages which causes a misprediction during this particular operation. Okay. As you can observe that if it goes into M1, then that means that there is no misprediction, and therefore, right, it does not cause any misprediction on if Di is equal to 1. Okay. On the other hand, if it is not equal to this, then it causes a misprediction, and since, right, you are comparing with Ti plus 1 1, that means you are basically doing it for the case or the assumption that Di is equal to 1. Okay. Likewise, right, M3 essentially contains those messages which does not cause a miss during the Montgomery multiplication of the I plus 1th squaring if Di is equal to 0, and it is an M4 consists of those messages which consists of the misprediction during the Montgomery multiplication of the I plus 1th squaring if Di is equal to 0. So, therefore, now the attack is very straightforward. So, we basically kind of have one online phase where the probable next bit is decided by the following observations. So, we basically kind of measure the average branch misses. So, this is observed by the actual hardware performance counter events, and the idea is that if the average of the bucket of M2, that means of all the messages which has gone into the M2 bucket, is more than like the average of those branch misses which has gone into the M1 bucket, then you find that what you are basically saying is that the average of M2 is more than the average of M1. Okay. So, you see that M2 actually causes a misprediction, and M1 it does not cause a misprediction. So, that means, right, this is kind of in coherence with what we expect, and therefore, right, it is more likely that Di is indeed equal to 1. Okay. On the contrary, if you would like to confirm your test, you can also compare with M3 and M4, and you see here the average of M4 is less than the average of M3. Okay. So, again if you come to M3 and M4, you see that here the average is of M4 essentially this is the misprediction and this is the no misprediction. So, if you get the like the average of M3 more than the average of M4, then for example, what you observe here, then that means that it is not in coherence with what should happen if di was 0, and therefore, it confirms that di is not 0. Okay. So, therefore, this test confirms that di is equal to 1 and this test confirms that di is not 0, and therefore, it kind of improves my confidence in the fact that the next bit is probably 1. And likewise, for the the opposite will happen when the next bit, when I would predict the next bit to be 0. So, with this basically attack setup, right, we basically have got this online phase or the offline phase, where you basically take all the Messiers and I use my simulated model to basically partition the inputs into the buckets M1, M2, M3 and M4. And there is an online phase where I basically do this comparison. Okay. Remember that when you are doing the online phase, you just have a bunch of hardware performance counters for the corresponding Messiers. So, you basically kind of decrypt using M1, decrypt using M2, decrypt using M3 and so on, and you basically get a bunch of hardware performance counter events. Okay. So, then you basically calculate these averages and then you make a decision about the next bit. Okay. So, you basically kind of do this attack in an iterative fashion. Here is an experimental validation for the attack. So, you see that we show here in particular an online phase of the attack, where the target is a square and multiply algorithm, which has been performed with 1000 iterations. So, in particular, this has been done on an Intel Core 2 Duo platform, and you can observe here that the first one shows that the correct assumption is di is equal to 1. So, it kind of shows that the average time for example, shown in the blue lines is more than that for the red ones, and the blue ones correspond, or the blue dots correspond to the fact where for M2, and what we see is that the average for M2 is more than the average for M1. And if you go to the algorithm, right, you see that the average for M2 being more than the average for M1, the algorithm predicts that it is equal to 1. Okay. The next bit is 1, which is indeed the correct assumption. Likewise, if you partition with M3 and M4, we observe that the average for M4 is less than the average for M3. So, the average for M3 is more, and here also you observe that if the average for M3 is more, then you basically predict the next bit to be 1, and therefore, indeed, right, the incorrect assumption would be di equal to 0, and this also confirms that the next bit is 1. Okay. So, therefore, this kind of accurately estimates some specific ith bit. So, likewise, we can perform this attack for other corresponding bits and retrieve the attack one by one. So, we can also perform the attack. So, here is the result on how the attack works on the Montgomery ladder. Again, like it is a similar kind of experimentation that we do, and you can observe that here the separation also can be observed, and it also kind of correctly estimates the fact that di is equal to 1. So, this attack, right, can also help. One thing should be kept in mind, that this is an iterative attack. So, if you do a mistake in one of the bits, then the attack inaccuracy would percolate. One way of understanding that you have made a mistake is that once you make a mistake, and if you would like to kind of discover the next subsequent bits, then you will find that the inconclusiveness or the confidence is pretty low. For example, like in the previous cases, if you have made the correctly guessed the previous bits correctly, then you would probably have something like a 90 versus 10 ratio, whereas here probably you will have something like 60 versus 40 or something like, which is essentially kind of inconclusive. So, this probably will kind of raise an alert that there is a mistake that you have done in the previous iteration. So, there is an inherent amount of like error correction involved in this detection mechanism. So, here is an example of how the like the attack works on a SEC256 curve. Again, this is an elliptic curve crypto system, and in particular, right, I am not going into the details, but what you can do here is that this attack is based on, say, double and add algorithm. So, what you can do is that you can target the double operation, like in the previous case I was targeting the squaring operation. So, here I will be targeting the double operation, and in the double operation, right, there are again subsequently several operations, and you can kind of choose any one of them. In particular, right, since there are more multiplications and all of them are doing the Montgomery reduction operation, so you basically expect that the separation would be probably even more clear. Okay. And that is again observed here by this observation. Here is an illustration of the attack performing or targeting an actual elliptic curve implementation of the NIST curves. So, this is the NIST 256 or NIST P256. In particular, the curve is called as SEC P256R1. So, here you can again observe that a similar attack has been demonstrated here, which essentially uses the technique that we have just now discussed. Just to mention, like in the previous cases we were targeting the squaring operation. So, here we are basically targeting the doubling operation. So, in the doubling operation now like in the squaring operation there was only one multiplication, but in the doubling operation there are several multiplications that you can target. In particular, in this attack we target the T1 Z to Z1 square as the like underlying operation. Okay, so there are 8 multiplications and you can target any one of them. So, we target one of them in the 8 multiplications in the double operation. Okay. So, also right, and since there are many multiplications, apparently what we observe is that the separation or the performance of the attack is even better on elliptic curve based implementations. So, likewise you can also perform the attack on Montgomery ladder, which we essentially know is a more balanced structure. So, here is an example to show that again how again we can perform the attack on a similar platform. For example, this attack has been demonstrated on an Intel Core i3 machine, and the offline phase for the Montgomery attack algorithm is slightly different from that of the double and add. Here 2 sub simulated traces are present depending on the scalar bits. Like in the previous case there was only one sub simulation which you are doing, but in the Montgomery ladder there will be 2 sub simulations which you have to basically take care, because of the fact that because you know that in one of them you are probably doing a doubling of you are doing it over, there are 2 registers and you are basically operating on both of them. So, here 2 sub simulated traces are present depending on the scalar bit, the next bit, and hence the partitioning of the inputs is done by selecting one of these traces depending on the guess of the secret bit. So, to conclude, branch mispredictions can be utilized as a powerful side channel vector. HPCs offer a rich source of information which can be utilized for attacking public key ciphers. The message is not to implement public key ciphers with secret dependent conditional statements, which we see are vulnerable to side channels and microarchitecture attacks. HPCs have been recently restricted for privileged users, and therefore, probably it is not easy to mount, or it is not so easy to doable to mount attacks directly using HPC values. Nevertheless, they provide important information for analysis and even raising alerts for possible side channel attacks. For example, once you develop this attack, you can probably try to redo this attack by just replacing the branch miss event with timing as a side channel vector. Okay. So, with this we would like to conclude, and the reference that we have used for this book is essentially shown here. It is Timing Channels in Cryptography, published by Springer. So thank you for your attention.